So these cantilever beams then, let's have a look at these for a second. Free end, there's a free end, so it's able to move freely. And what we say is that the bending moment is 0 at the free end. So our bending moment diagram is going to start at 0 at that free end. To find the reaction, this is the only place we're going to feel a reaction. What's this reaction force up at that point? Well, it's just a case of using the total downward forces must equal the total upward forces. So I've got 30 plus 20 plus 10 is 60 kilonewtons down. So there must be a reaction force of 60 kilonewtons at that end. Otherwise, it would either be moving up or down. So to find the reaction force, that's straightforward. Because we haven't got another support here that can take some of that force. We haven't got two supports anymore. We've just got the one. So that's got to take all that up force. We're going to find that the bending moment ends up with a concentrated moment at this end. There, at this end. A concentrated anti-clockwise moment to counteract the moment due to each of these going around the beam. And that's what we're going to end up with when we do this. So if we look at this shear force and bending moment diagram we have here, actually, if you could just get hold of this line on my diagram and just move it up a bit, it would be handy, okay? And get hold of this one and move it down a bit. I should have put them a bit further apart because I think intuitively our shear force diagram, we're going to start off with a shear force coming down here of 10 kilonewtons. And then nothing is going to happen until we get to this point, and then it goes down another 20. And then nothing is going to happen until we get to this point, and then it's going to go down 30, and we're going to end up at this point here with our reaction force. So it'll be 10, 20, 30, 40, 50, 60, and then the reaction force takes us back up to 0 again. So the shear force diagram is straightforward. However, conventionally, and I don't really understand why, because intuitive to me it should be that way because it's going down that way. But often they're drawn, and that's why your lines are sort of together with this above. So let's use yours as you've got them already. But instead of drawing these below, let's draw them up. So it starts up here, and we've got a reaction force of 10, and then a reaction force of another 20, which takes us to 30, and then 60 by the time we get to here. So that's 60, 10, 30. Gives us our shear forces. Now the bending moment diagram starts at 0. The bending moment at the free end is 0. But it's not going to end up at 0. We're going to end up with a concentrated moment at that end. And that will be the point of maximum bending moment, because that's where it's being held at this end of the beam. So all the moment's going to be concentrated at this end here. And so we're going to end up with our maximum moment at that point. So it's different to the previous examples where we had a supported beam in that sense. But apart from that, the same rules apply. We start at 0. We can find the area underneath this curve, the shear curve. The value of the shear will give us the gradient. So again, intuitively to me that's wrong, because this is a, and that's possibly why, because we're coming down here now, this bending moment, and that's going to be a positive gradient. So this gives us a positive gradient of 10, which takes us to this point. And then we're going to end up with this area, will take us to this point down here, wherever that is. That will be a steeper gradient than that, so I didn't draw that very well, so probably do something like this. And then final point will take us to our maximum point of bending moment, and that will give us our concentrated moment at that point. So that's our interesting point. So we're going to end up with a series of lines that go down here, given by these areas. So find those areas and work out where you end up with, and that will be your maximum bending moment. I'll just pause while you do that. So hopefully you're going to end up with something like this. The area underneath this one is 10 times 1 metre, so that takes us to this point here. The area under here is 30 times 2 metres, which is 60, so that takes us to minus 70. And the gradient is a straight line with a gradient of 30, so it's going down 30 and then another 30 to get us to minus 70, and then finally down to a maximum concentrated moment of minus 130 kilonewton meters is the maximum bending moment, the concentrated bending moment at this point here, going around there. If you think about it, we're starting at this end and then moving this way when we think about it. And if we think of it about this point here on the diagram, which is this point on the beam, it's as though the bending moment at this point is actually equal to the moment due to the weight of what's to the right-hand side of it. What's the bending moment at this point? That's due to the weight of everything this side of it, pulling it around this way. So the concentrated bending moment going back this way is due to the weight of the beam to the right of it. So it's going to gradually increase more and more and more until you get to the maximum bending moment on the left. So that sort of explains the idea of it. So again, we can work out what the moment is at any point along the beam. Okay, stop there.